All right, so I'll take a quick look at the homework 6 description, and then I want to talk about medium access control for Ethernet and perhaps for Wi-Fi, and we'll get to some details of how Ethernet works, various components and things. Yeah?
Will the grades for homework 3 be out soon?
Four.
Yeah.
I would think so, yeah. I think Ahmed told me he had graded them, and we had some discussion about some details. He might regrade that, and then, yeah, should be out any minute now. any day now. All right, yeah.
Are we going to go over homework 5?
The solution for homework 5. I'm not prepared today. Maybe we'll do it on Wednesday. Yeah. Right. Okay. So, what was I doing? Yes. So let's take a look at yeah.
Was last lecture recorded?
Yes, it was.
Okay.
Did I not post it?
It's not up yet.
I will post it. Thanks for the reminder. Right. What? Stop that. Okay, so a couple of details left to iron out for the homework 6 description, but the general idea is we're writing this raw socket application. Right? It happens to be a ping tool. That aspect isn't that important. We'll do a couple of different ways that you can ping that you wouldn't do if you're writing a ping using just ICMP socket or just ICMP. So a raw socket is, it works like any other file descriptor, sort of like a normal socket, except you can't connect it. It's a little bit more like a UDP socket in that sense, yes. And what you get is not UDP application payloads, which we've done before. No, instead you get an entire Ethernet packet. Right? So you get to both receive and send entire Ethernet packets. That means you've got your Ethernet header first, and then your IP header, and then whatever protocol comes after, whether that's TCP, UDP, ICMP. Trying to remember if ARP has an IP header, I would probably not. And anyway, so those are raw sockets. There's a very handy little page here that talks about raw socket programming. Lots of good stuff there. Very important, we're using AF packet. It's not AF inet. AF inet gives you raw IP packets, which means they're going to skip the Ethernet header for you, take care of that. But in this case, we're doing the entire stack of headers. Okay, so the challenge here is basically just getting packets to work on the network because they need to be correctly formatted, and then figuring out, oh, what should all the addresses be? All right, we try to ping a remote address. Well, what's the destination Ethernet address for some random IP address, right? So for this, we need to read a few different configuration tables. Basically, you need the routing table to know where a packet should go. You need the ARP table to know what is the Ethernet address of my next hop for this destination. And you also need to use what's called an IO control or ioctl to just learn, oh, what's my local address? What's the IP address of my network interface so that the response can come back? And what's the Ethernet address of my network interface? So initially, we'll have a manual ping, right? So you basically just need to assemble the headers. It's a bunch of structs. Should be relatively straightforward for you at this point. And then you already provide sort of on the command line the correct IP address and Ethernet address. Those are easy to find for a local destination. It's easy to figure out what these addresses should be. just on the command line. You run ifconfig, you run route, maybe you ping it, and you see what comes back, that sort of thing. So here it's highly manual. Later on, we then change this. Right? So if it works for a local destination, like this, then later on you can change it to work for a remote destination manually again. If this is your local gateway, the one that goes to the internet, then a ping for any internet host will work in this field. Okay, so here we're sending ICMP echo requests. Next step is we want to sort of make all that automatic. So now we're getting rid of everything, all of these, except for this one here. The destination IP address is still there. We want to be able to ping any address. But then now we have to figure out, oh, what are the correct other addresses we fill into the headers. And then finally we have a TCP ping where we do basically the same thing, except here we also we send a TCP request, a SYN packet, or maybe not a SYN packet, maybe any packet, and we see if we get a response from the other side and report on the latency of that. And sometimes you will get ICMP error message back instead saying, oh, route unreachable, host unreachable, network unreachable, host unreachable, port unreachable, and we'll report on those errors back. Yeah.
I know it's to be determined, but does the TCP thing have to be done with raw packets too?
It is not. I mean, yes, you should do it that way. In principle, you can do part of it with connect. If you were to implement this not as a homework, you could probably make a TCP socket, try to connect, have a short timeout on it, and then you could see, oh, does it respond? I don't think that you would be able to get, let me try something. Let's see. Yeah, sorry. So this is the gateway for the 34 subnet, right? All the addresses between 1 and 255 here. So it responds to ping, but does it respond to TCP ping? Yeah. So I guess this is probably like using the error code that you would get from connect will say -1, and then maybe you can get the error message out. In our case, we should do it with ICMP. We already have ICMP parsing in the application, so we'll just add that on top. Okay, so yeah, so in principle, you can do some things, I think, with TCP sockets. I haven't really tried it to know exactly. Yeah, so you would be able to you'd be able to try with a SYN, but you would never be able to try with an incorrectly formed, like a TCP packet from the middle of a stream, let's say, which is something that we should try as well.
So you're not trying to establish a connection, right? You're just sending a SYN packet and just seeing the response time of the.
Yeah, right. So we're trying to kind of trick these remote nodes. There's some hosts that just won't respond to ping, but they would have to respond to TCP. And then question is, oh, maybe do they respond to a SYN packet? Maybe, maybe not. Do they respond to some other kind of malformed packet? We'll try a few different things and see what comes out. I'll put in the details here, and I'll have to experiment with myself to make sure that it works as expected. Right. Okay. So I think the main thing we're learning out of this is just sort of how all these headers fit together, and the routing table, and the ARP table, and all these things going back and forth. You're not expected to send ARP packets. Like, everything should be in the table already. And you can experiment with TCP dump. It's very good. Just to see that, oh, the packet I sent, it actually looks like what I thought it looks like. And to see when you get a response, so you don't have to read responses from the socket until you start actually getting valid responses as verified by TCP dump. And oh yeah, this is a really handy little tool too. If you haven't used it already, strace just prints out for every system call that an application makes. So let's just try it. So here, let's see what ifconfig does first. Right, it spits out all of this output for every interface. And now if you say strace ifconfig, here we have everything we're writing out and everything we did. Let's do something here. Yeah, so here we're actually looking at, oh, what are the interface flags, right? That we're reading the flags, we're reading the hardware address, this one. We're reading the MTU and so on. This is everything that we need in order to spit out these strings that come out on the command line. Really handy overall to just understand what a program is doing. There's some good directories in here that you need to be aware of. And, so here's the ARP table. Right. That is a pretend a pretend file system. I don't know if you've taken the operating systems class. We sometimes have a homework that makes this sort of thing, where these files don't exist. Like there's nothing on disk. The OS just kind of gets a read system call and it says, oh, they want to see my ARP table. Fine, I'll spit out the ARP table. Right. This is the cache of all of the MAC addresses of nearby IP addresses. And similarly, here's the routing table. Right. So for this destination, yeah, sorry about the formatting. This is hex. These are IP addresses in hexadecimal format. That's just how Linux likes to spit it out. But you can parse it with scanf. Right. So this is default gateway. Right. For every destination except for these subnets, here's the gateway one should be using. That's the IP address of the gateway. All right, so get started on just kind of getting the raw interface to work for you, and then we'll talk about like the little specifics.
Is there going to be a skeleton code for this assignment?
Yeah, it's the skeleton code is essentially what is from the that website I showed you. Let me see. In fact, let's just leave it like that. And there's a link to it. Let's see. Right here. Sorry. There. Okay. So this one has quite a bit of code, like how to receive packets, how to send packets, how to deal with the various headers, let's see, what the headers look like, and so on. So I think you'll find that very helpful. Yeah.
So if we take from there, do you want us to put that like in our source?
Yeah, this is fine. I mean, it's kind of implicit for this one. Yeah.
Yeah, it is.
Yeah. Good question.
Also, it will be due 2 weeks.
2 weeks as usual, yeah. Right. Okay, so I wanted to talk about multiple access control. So again, we have this network, for now a wired network. And dig up the pictures. Too many drawings lately. Sorry. Is that it? No. Ah. Damn it. Where are my drawings? That's the one. Okay. Right. So we have this Ethernet network. There's a cable going between us. We can all overhear everyone's transmissions. And in this case, we can, our interface can listen at the same time as it can transmit. This is not true for radios. Radios are a little special, but with cables, generally speaking, you can your receiver can be active at the same time as your transmitter. The received power is roughly, I think the reason is that the received power is roughly the same as the transmitted power. Someone else transmits something, you get about what they transmitted, whereas on a radio you get like a billionth of what they transmitted or something like that. And if you try to transmit something at the same time, it kind of overpowers everything. Okay, so the question is, we have these 4 potential transmitters on the network at the same time, and contrary to what we discussed before with the sort of pre-agreed upon time slots or channels or something like this, now we want to have a sort of opportunistic random access to this network. Whenever you want to feel like sending something, you basically just go ahead and send it. The main advantage of that is that now if most of these nodes have nothing to send and this one has a lot to send, then it gets to use most of the network, which isn't true for a TDMA style network. But as we saw last time, if they just go ahead and transmit whenever they feel like it, and they don't do anything more clever than that, then you end up with very poor utilization. And in the best case, you end up with 18.4% utilization, theoretically speaking, all same length transmissions and all that. And that being basically because either you're not sending enough and everything's fine, you're getting transmissions through, but you're just not getting enough transmissions through, or you're sending too much and now you're all colliding and nobody gets anything through. And there's kind of a sweet middle spot there, and the best you can do in that sweet spot is 18.4%, according to this sort of theoretical result, the Aloha protocol. So something somewhat similar that they're doing in Ethernet is called carrier sensing multiple access. So here the idea is we don't just blindly transmit, because we're not using radios. Actually, maybe that's not quite true. Radios or not radios, doesn't matter. Don't just blindly transmit. Before you transmit anything, listen to the channel, see if anyone else is sending. If someone else is sending, don't send. Right? So in this case, we're in pretty good shape. Like now we're not going to have very many collisions. General idea. Don't send if someone else is. So this sounds pretty easy. The reason they don't do it in this Aloha thing is that for island-to-island communication, it's not at all obvious when someone else is transmitting. It's easy if it's 2 islands. In fact, let me draw this. Let's do this Aloha thing again. Square islands. So it's easy if I'm sending to here and this one's sending to there, right? You can at least conceptually imagine that these radio receivers could hear that this guy can hear that that one's sending, so I keep quiet. But it's not usually the case that you have only 2 transmitters in such a network. So there could be actually, let's go the other way. So now the question is, does this island hear that this one is sending, right? So there's an ongoing transmission here, and I want to send. Well, I can't hear that anyone else is talking, and so I'm just going to go. So that's sort of the Aloha setup. In the Ethernet setup, everyone can overhear everyone else, and this is called, we're all in the same collision domain, yeah, let's call it a collision domain. So now we know what's going on in the network. That's realistic for a small network, but not necessarily for a sort of large, wide area situation. Okay, so if nobody else is sending, don't. If someone else is sending, don't send. That's fine. But what about if someone is sending? Like, when do we start sending? Yeah.
I have a question about that picture.
Yeah.
With the other one.
Oop.
Two different.
Yeah.
So doesn't that kind of imply that the collision domains are different?
Yes, here we have different collision domains, or at least like these two can't overhear each other. Right? And so that means that we can't use this listen for other people to see if other people are transmitting, because we can't hear them. It's kind of a common situation in Wi-Fi. Actually, maybe I don't quite understand the question. I guess.
So the receiver can only listen to one person at once?
No, that's not it. These islands are far apart. Actually, let's draw it a different way. Let's draw it like this, and I'll just skip the other edge. Right. So there's a certain range. The radios can reach a certain range, a certain distance, and now this receiver is here. They can receive the signal from both of them because this is the maximum distance of the radio, right? But then this one can't hear anything if this one's transmitting, so it can't decide whether to transmit based on hearing someone else transmitting.
I don't see why they both can't just transmit, because they can't hear each other. I'm not seeing the problem.
Oh, I see. Okay, yeah. So the problem is that at the receiver side, there's a collision. Both these two signals, like in the previous examples we've discussed, like if you have two transmissions at the same time, you just get garbage. So the receiver gets garbage. At the transmitter side, it looks pretty good. Right? It's a nice clean signal because there's no one else talking, but over here it's no good. I think you could experience that in you're in the bathroom, you're flushing the toilet, right? If you're saying something, whoever's far away, like in the other room, can hear you. But if they're saying something to you, you can't hear them because the toilet is too noisy, right? You're getting kind of a weaker signal from them, but in the other direction, the toilet and you are equally weakened by the distance. Okay, so anyway, the transmissions can never overlap in time, or we get garbage. This is not true if you're using different channels, different radio frequencies, different cables. There's lots of different media. If you do it in air as opposed to in radio, right? There's all sorts of ways to split up a transmission, but multiple access is all about sharing one such channel. Okay. So now the question is, when do we send if someone is sending? Right? There was an ongoing transmission, and then should we just send after? Right? So you can tell, oh, transmission has ended. You just keep listening until the other guy stops sending, and then you go for it. What do you think?
Could there be a end of message kind of?
Oh, okay. Sorry. So this is carrier sensing. The general idea here is your receiver has the capability of getting more than zeros and ones. They can also see that, oh, a transmission is ongoing. I should have clarified that. I guess the PHY layer provides us sort of one other bit, kind of a long-term bit here. There's power in the channel. So we know when it's finished. This guy stopped sending. And usually it's a good idea to have a little, it's called a frame gap of some short duration, just to make sure that things don't overlap. There could be different So in this case, for example, these two radios are a different distance from this island. And it's good if they're all kind of, there's no chance of them overlapping because they are different distance. Like light arrives a little slower from one island, the one that's a little further apart. So we have a little frame separation just to make sure we don't get any accidental overlaps like that. Okay, but so after the transmission has ended and this frame separation period has passed, call it a few nanoseconds. Let's see, so in 1 nanosecond we get 300 meters, 900 feet. That's probably enough. In a Wi-Fi setting, in an Ethernet setting too. You don't need cables longer than 900 feet. Right, so what do you think? What happens? There's something horrible about this idea.
More than one person might want to start transmitting.
Exactly. So now everyone's listening for the end of this transmission, and then at the same time, 1 nanosecond after the transmission, they all send it. Right? That's really not right. So there is an extension. It's called collision detection, where you also listen while you're sending. You listen to see if anything else came in at the same time. You can apparently do that, right? And at least in some media you can do that. And then you could stop transmitting. So there was a collision, and you detected the collision, so you stopped transmitting, and now there's a sort of a shorter period of waste when we're all just transmitting and overlapping. So that's good. But it would be even better if we didn't collide in the first place. What might we do? Yeah.
Maybe the receiver should pick who's going to transmit that.
Ooh, the receiver. But we don't know who the receiver is. So this is not the setting. This is the setting. So all of these guys at some point have something they want to send to someone, and we don't know who yet because they didn't transmit it. Yeah.
Each sender could have like a different time that they wait before they send it. They would signal kind of like a priority for them.
That's a cool idea. Right. So every transmitter gets assigned a priority. I wait 1 slot, you wait 2 slots, he waits 3 slots, and he waits 4 slots. And a slot is maybe one of those frame separation intervals, right? A nanosecond. So now everyone, actually not everyone gets to take their own turn because I want to send every time. So it's awesome for me, maybe not so good for the other ones. There's actually another way, and while we're at this, there's a nice similar looking scheme. It's called token ring. You may have heard of token ring. It was kind of a popular protocol quite a while ago now, 20, 30 years ago. So now there's this token. It's not really something that you're passing around, but it's sort of a my turn somehow. So now this guy holds on to a token. He knows that it's his turn. So while it's his turn, he sends some packets. Everyone else knows that, oh, they don't have the token, so they don't get to transmit. And then when this guy is done, or after some period that seems reasonable to the system administrator or to the protocol designer, maybe 10 packets, I don't know. After 10 packets, this guy says, okay, now it's your turn. So he sends another little packet that says, okay, next transmitter's turn. And then they form a ring. So it's just like the next guy here. So now they send 10 packets and tell the next one it's their turn, and so on. What's really nice about token ring is that you can't have any collisions, right? Whoever has the token has it's sort of a lock on the entire channel. Like, I'm the only user. And it's perfect utilization, almost. If this next sender has anything to send, they get to go right after they get the token. If they don't, they just forward the token immediately. So it's very efficient in that sense. The problem is that it's a little complicated. And if you have a buggy device on the network, it can really be a big problem. Right. So now you plug in this cheap thing, like you got something from a friend that was supposed to make cool lights or something on the network, and gets the token, and then just drops it. It forgets to forward it, right? And no one's going to send any more packets. So that's, of course, they thought about that. So then they came up with some recovery protocol for when there is no token anymore. Who's supposed to create a new token so you can start running? And if by accident there's 2 tokens on the network, how do you kind of restart and so on? So it, excuse me, it got really complicated, and they kind of dropped it after a while. Like, let's do something easier. But it is really efficient in a sense. Okay, so let's not do token ring, and let's not do that fixed priority. That seems like I mean, it's not clear that I'm just going to use the channel. Like, if I have the highest priority and I have stuff to send, well, I really should be sending until I'm not the highest priority in some sense, but I would have to yield my priority then, and now it starts getting complicated again. Okay, any other ideas? How can we make sure that only one of us use the network or use the channel? Actually, we don't have to really make sure, right? We just have to say with high probability, only one transmitter tries to send next. So how about we just pick a random number? Right? I pick a random number between 0 and 4. 0 and 3, I guess. It's 4 numbers. Right? So I pick a random number, and after that many slots, I start transmitting. Maybe 0 and 4 is a little small. So let's do between 0 and 16. Right? We all pick a random number, and after that many empty periods, we go for it. And if someone else starts before us, well, then we start over. After they're done, we start another trial. So now the bigger the number, the bigger the range of numbers, the smaller the probability that we collide. Right? If there's only 2 transmitters on the network, we probably should have a small random number. And if there's many transmitters on the network, we probably should have a large random number. And if it's large enough, we're going to have actually, if it's about right, we're going to have a low probability of collision, and we're not going to be waiting for too long on average. You could imagine, like, if you have 0 to 1,000,000. There's only 2 transmitters on the network, and it's 0 to 1,000,000 is the range. So now we wait 1,000,000 transmissions. Every now and then we may wait 1,000,000 of those little nanoseconds. So that's a whole millisecond now that we waited just to transmit. That doesn't seem quite right. So we somehow have to decide how long, like, what should be the range of numbers for this wait. It should be based on how many nodes there are in the network, but measuring how many nodes there are in the network, that's really difficult. Any ideas? Yeah.
Could it potentially be a function of, like, the frequency of packets being sent to the network rather than the number of nodes in the network?
Oh, that's interesting. But so if there's only 2 nodes and they're sending a lot, there still should only be a relatively short sort of window that we pick delays from, right? Yeah.
I was going to say, start with the range being small, and then try it, and then if there's a collision, maybe double the range or something.
Exactly. All right. So now we have a sort of a binary search here for the size of the network. We're trying to estimate the size of the network so that we can then back off an appropriate amount of time, so that we always have someone who picks about 1, right? But we don't all pick about 1. We pick something, usually we pick something bigger, but only one of us ends up getting the 1. And if 2 of us ends up getting this 1 a lot, well, then we should have a bigger range so that we don't have collisions so often. So every time we have a collision, grow the range. Yeah, that's actually the Ethernet design. So First you have a really small one, you wait for a little bit, and you try it. If it doesn't work, then you increase the range and pick a random number in a bigger range until you stop having collisions. Yeah?
How do the different devices agree on how to increase the range?
They don't. When they observe a collision, they increase it.
It just seems like there's room for like malicious behavior.
Ooh, absolutely, yeah. It's really easy to be malicious on an Ethernet. You don't have to play with these numbers. You just send some garbage all the time. Right? It's over. You don't have to send bits or anything. In fact, you can do better. Just plug in a high voltage source and you fry all your other guys. Right? But yeah, so generally with cables, you kind of have to trust people. And you only plug in devices that you want to use. And sometimes they will be buggy, right? But they probably will not be malicious. Yeah, and you basically have to live with that. Okay, so that's CSMA, carrier sensing multiple access. In Wi-Fi, it gets more complicated. We should do a whole lecture on that. I want to talk a little bit more about Ethernet, since we're on the topic of Ethernet. So let's see. We've seen the Ethernet frame format. Do that again. Basically, source address, destination address, data, and type. This is actually kind of gets a little bigger than this, but basically says is there's an Ethernet packet coming. There's a preamble there, and that's similar to the thing we were talking about before, the frame start delimiter, right? So the preamble is a bunch of bits that say this is the beginning of a new packet. It's handy not only because, well, you can kind of tell at the beginning of a transmission. You can tell that from, oh, there's power on the cable. But you really want to know which exactly is the first bit. You don't want to be off by anything. So the preamble is like a 01010101 for a little while, and then 00, and now you know, like, okay, let's start receiving data. It consists of, there's a few different sort of file layers for this. The first one for Ethernet looked like this. This looks a little bit like your Ethernet, sorry, your coax cables that you have for cable TV. So it's this one copper cable in some sort of protective sheathing, and all of the various devices hook into the same shared medium. This is the origin of this CSMA and Ethernet, like they're sharing one copper cable to do all the transmissions. But this has changed. So over time, it switched over to this twisted pair copper wire, like this thing. There's eight little cables inside, and they're twisted because that happens physically to make the interference less and things. But basically, 8 little cables inside of a bigger cable. And they can be then connected to a variety of little devices in between to kind of create more of a tree topology. A hub, like this, basically just retransmits the signal. It doesn't read the packet or look at the headers or anything. It just kind of gets voltage and transmits voltage out to the other ports. A switch is a little bit better. See if we have a... okay, I don't have a picture of it, but a switch looks exactly the same. I'm sure you actually, let's do a... I'm sure you've seen these guys. So basically all of these ports are the same. A packet that comes in through one of the ports, the switch reads the entire packet, looks at the destination Ethernet address, and tries to remember, like, oh, which port was that address in? All right? So now we have a little lookup table, a switching table, sitting inside this piece of hardware, and it remembers that, this is awkward. Okay, look at the little hand here, not at the zooming, moving picture. So a packet comes in here, and the switch will only transmit it out the correct port, number 4, right? Because the destination happens to be connected to port number 4. How can a switch know that a destination is connected to a certain port?
Hard-coded?
It's not hard-coded. So the destination is a MAC address, right? Well, it's hard-coded in the destination. The destination has it, but how does the switch know it? Yeah.
Does it announce itself when it's plugged in?
In fact, it doesn't. I think it should. That'd be nice. Actually, it doesn't really solve it either. No, the switch will just listen for traffic. So if I send any packet to this switch, it'll have my source address in it. So the switch remembers, oh, this guy's on that side. The problem, you could imagine announcing, like, but what if you have a network that's a little bigger? So here we add we add another hub or a switch here, and then we go over here. So now I announce myself. The announcement would come to this switch, that's great, but then we'd have to forward it to the next switch and say, oh yeah, I know that this guy's over here too. In a larger network, it starts getting pretty chatty. If we're not sending any traffic to all these other remote switches, we probably shouldn't be announcing our presence either. That's sort of the argument. There's only so much room in a switch table in one of these switches. You can have an Ethernet network of hundreds of thousands of devices, so we really want to limit the amount of state if we can. Let's see. So it looks, let's see. I have a good switch table picture. Right. So basically it'll look something like this. So you have, oh, for a certain destination address, which interface should I send it out? And it's not clear that the destination is at, like, just on the other side of that interface, but it's somewhere down the road on that interface. So if I've ever received any traffic in my direction, then I know which way to send it. And then you have a little time saying when you last heard from it, so you can purge the table from old entries. After someone unplugs, we don't want to use up state in the switch. And what if we don't know? Yeah.
Could it send out that broadcast where you ask if anyone knows about that specific address?
Yeah, in fact, it's better than that. It doesn't have to.
Well, I was thinking that if it got some message from something, it would store it in the table, but I don't know.
Yeah, so if it ever got anything from a destination node, it would have it in its table, so it knows where that node is. But now, the question was, if a packet comes in with a destination address and we don't know don't know which way to send it. Yeah, you could imagine sending an ARP request. But now we're asking about which machine has this IP address. And that's what ARP is. So an easier way is to just send it out to all the ports. And with any luck, a response will come back after a little while, because usually protocols are like two-way. And so now we get a response back from one of them, and now we know which way to send it next. Usually, we don't even have to do that, because whoever sent the packet had reason to send it. Like they somehow figured out which is the MAC address I want to send something to. Usually to do that, they use an ARP request, right? So there was a broadcast already. Oh yeah, if the address is FF, then it goes out all the interfaces. Right? That's how you do an Ethernet broadcast. Pretty straightforward. But anyway, you made this ARP request, and you got a response saying, yeah, this is my IP, I'm this IP address, and here's my MAC address. So now the switch already saw that packet coming through, so the switch already knows where the destination is. Right, so a really nice advantage of Ethernet with a switch in the middle here is that every cable is its own collision domain. So there is only ever 2 transmitters on any given cable, and they never collide. I mean, yes, I guess in principle they could collide, but usually there's also this full duplex Ethernet. So in fact, you can't collide. You can transmit in both directions on these 8 cable Cat5 cables. So there can't be any collisions. So you don't really need to worry about the carrier sensing on wired Ethernet. You have a dedicated channel just for you. A bit of a problem is when the network grows. So the larger the network, the harder it gets to keep track of where everyone is. And every time there's a broadcast, it goes all over the place. So if you have 100,000 nodes, there's going to be a lot of broadcasts, and everyone's receiving that broadcast packet. So to make things a little more scalable, we usually end up using routers, which are IP devices, right? So now we're not on the same Ethernet network. So here's one Ethernet network, and then we put another Ethernet network on the other side. No Ethernet traffic makes it from over here to over here. Right? So an IP broadcast, sorry, an Ethernet broadcast would stay constrained to one of these Ethernet networks. So that's generally the preferred design. You use reasonable sized Ethernet networks, hundreds of nodes maybe, and then you divide those up. If it gets any bigger than that, you divide it up into multiple Ethernet networks with IP routers in between, so that you don't get crazy amount of broadcast traffic. Okay, let me see if I had. No, that wasn't it. Okay, no, we'll leave it there. So next time, I think we'll talk about Wi-Fi in lots of detail.